What's up, AP Calculus students? Mr. Ford here with another homework tutorial. I'm actually a bit ahead of the game today. We're looking at 6.1.2 problems 23 through 29. We're going to be doing all of the problems here, although 623 gets an asterisk next to it because what I don't like about this problem is the amount of puzzling you would have to do over what the actual function is. But I do want to walk you through a question that could be fair game for your AP Calc test, and that is to maximize or find the maximum of a function. That's exactly what we're going to do here. We have an electronics store purchasing stereos from a supply company at a cost of $63, and they sell them for $99, which means their profit is currently $99 minus $63, which is $36. They're making $36 basically on every stereo that they sell. At this price, they're selling 23 per week. So currently, you might think about this, their current profits are 23 computers times $36 per sale. However, marketing studies show that for each $2 decrease in price, the store will sell an additional 5 stereos, and that is what is going to lead us to the actual function, which I'm just going to give you if you're watching this video, and I'll give it to you in class also. This takes the existing $36 they sell it for, and $23, the 23 computers or stereos they sell, and X in this case is the number of $2 drops in price. Now, the writing of this actual function is beyond the scope of the calculus class, which is why you don't see these problems on AP Calc tests anymore. They were scrapped with a couple decades ago because it was determined that the amount of work going into this problem is heavy on algebra, not on calculus. Calculus comes in when they want us to maximize these profits. Now, again, you could easily do this problem by just graphing it and seeing where the maximum happens, but we're going to do this with calculus anyway. We're just going to kind of fly through it. The first thing we got to do is actually expand this out. 36 times 23 is going to give us 828 minus 46x plus 5 times 36, which is 180x. Minus 10x squared. And our objective here is to make this equal to 0 because that's the original profit function, p of x equals negative 10x squared plus 134x plus 828. And what we're going to do here is we're going to find the derivative of this, p prime of x, which is just negative 20x plus 134. And since this is a pretty easy quadratic, what we're looking for is when this equals 0. The quadratic equation has a derivative that is a linear function, and the linear function only has one 0. That's going to happen whenever 134 divided by 20 happens. I'm not sure what that is, but that's where it happens, and that's going to be 6.7. And since there is only that one critical value, and since our original function is a parabola with a negative thing there, we know that it's going to be an opening down parabola with a maximum value. Or another way to think about it, if you were to take the derivative of this, you would get negative 20, which is always concave down. So we know that x equals 6.7 is a maximum. So we should, I guess if you're thinking about this, if x is the number of prices that we should increase it by, then we should think, let's see, we want to take our 36 original dollars we're charging and subtract 2 times 6.7. 2 times 6.7. So we should be charging $22.60 for each stereo. And at that price, we can expect to sell, oh, my calculator cam is all blurry. You can't even see what I'm doing here. At that price, we should expect to sell. Let's see, focus. You can do it. Hang on, I gotta maybe open up my dot cam here. Yes, can do it. Autofocus. There we go. At that price, we should expect to sell 23 plus 5 times 6.7, or 56.5 computers. If we multiply those together, we'll get a maximum profit of 1276.9. That problem's not super important to us, but I mean, because you will see a question like this probably on your calc test where they'll give you a function and expect you to find the maximum, but you will not be expected to write the problem based on the worst story there. Those are out. Let's get back into some more just straightforward algebra kind of math problems here. 624, we're going to decide if differentiating the following expressions requires product, quotient, chain rule, or a combination, and we're going to evaluate the derivatives. In this case, the first one is just a straight up chain rule, because the derivative with respect to t of the f of t squared is a separate function inside of f of t. B is going to require the product rule because x and h of x are both functions of x. And C is going to put them together. We're going to need the product and the chain rule. We've seen these on a few tests and quizzes at this stage too, so we'll get used to them here. These are not difficult to put together. So the derivative here is f prime of the original inside, f prime of t squared, times the derivative of the inside, times 2t, like that. The product rule in part B, well, let's see, it's the original first times the derivative of the second, h prime of x, plus the original second, h of x, times the derivative of the first, which is times 1, which you don't need to write down because it doesn't do anything. So that is the derivative right there. And over here, we're going to have the product and the chain rule put together. So let's try that same pattern again. The product is the original first, t, times the derivative of the second, which in this case is going to be the answer from part A, h prime of t squared times the derivative of the inside part, 2t, plus the original second thing, h of t squared, times the derivative of t, which again is just 1. So you don't need to write down the times 1. That's honestly, I mean, that's pretty cleaned up, but we can do a better job than that. How about 2t squared h prime of t squared plus h of t squared? Just like that. We'll combine a few things together. I like that answer. Okay, let's move on to y-kit. Way-kit, still looking for ways to rewrite expressions with exponents. This is going to be a review of your pre-calc algebra 2 days, thinking about derivative, or not even derivatives, just exponents. What we're doing here is we're recognizing that 2 to the 5 plus 3 power is equal to 2 to the 5th plus 2 to the 3rd power. That's a really handy algebra trick there. That is true. A lot of times we would add the 5 plus 3 and get 8, but we're seeing that in its bones. He wants to simplify 2 to the x plus 3 power, but needs your help. Well, if you follow the same pattern, you're just going to have 2 to the x times 2 to the 3rd power. That's the way you want to write that in part A. 2 to the x times 2 to the 3rds. So the question here is 2 to the x plus 3 proportional to 2 to the x? Proportional means that you can write it as a multiplication, a times 2 to the x. And you totally can. In this case, you have 2 to the 3rd times 2 to the x. The constant being multiplied is 2 to the 3rd power, which is just 8, if you really want to think about it that way. So yeah, 8 is the proportionality constant in this case. I guess if I'm being consistent, I should put k over here, because we think about proportional situations as k times something. That's a proportional. In this case, the constant is the 2 to the 3rds, or 8. Let's use the same method to rewrite 3 to the x minus 2. How about 3x over 3 squared? In this case, we have to divide. In order to get that subtraction, we need to divide the two things that are being raised to those powers. And for the other one, for 5 to the x plus 4, that's going to be the same thing as it was above, 5 to the x times 5 to the 4th power. This is a really handy way to rewrite things. We'll be using it a lot later on in this chapter, so we're setting up a preview idea right now. That's very important in this chapter that you do, or at least look at the homework questions, because this preview is going to be assumed that you've done it. Does the method work on 3 to the 2 times x power? That's going to be a hard no. We do not have an exponent rule for rewriting this thing. There is not really a handy way to do that. It's pretty much done exactly the way it can be done. There is no way to simplify this, because it's the adding of things doesn't happen here, so you don't get that same multiplication trick. Looking at 626, examine the following derivatives, consider multiple tools available for differentiation, and use the best strategy. So what we're going to do is we're just going to think about things here. We have added e to the x to our arsenal at this point. We haven't done it yet in my real life recording this video, but we will have done it in class by the time you see this, so that'll be nice. That's a nice thing to add to our list. Anyway, this is just a product rule in this problem. It's the original first, the sine of x, times the derivative of the second, which is e to the x, plus the original second, which is also e to the x, times the derivative of the first, which is cosine of x. And so, honestly, this is pretty much done. E to the x sine x plus e to the x cosine x. If you want to be real fancy, you could factor in e to the x out. But any one of these answers is acceptable for part A. For part B, we've got a quotient rule. Yeah, I was thinking maybe we could factor something out and actually make it simpler. But no, we are going to need to use the quotient rule for this one. So I'm going to try to fit it in this little space right next to B, because it's not too much to write. The top is 6z plus 1. the bottom is 3z minus 2. du is just the number 6, and dv is just the number 3. So this is a pretty straightforward little derivative to do here. So the derivative will be the original bottom, 3z minus 2, put that in parentheses, times the derivative of the top, which is just 6. That's these two right there. And then the next thing, minus the derivative of the bottom times the original top, 6z plus 1. I guess I'm changing the order around just to make it a little simpler to evaluate later on. And on the bottom, you're going to have 3z minus 2 squared. Honestly, I would walk away from this, but let's talk about how to simplify it. It's not too tough to do. You'd have 18z minus 12 minus 18z minus 3. Look at that. The 18z's cancel out. That's kind of groovy. Over 3z minus 2 squared. So the 18z's actually go away, and you end up with negative 15. Negative 15 over 3z minus 2 squared. I'm looking at the published answer in the book, and they write negative 15 times 3z minus 2 to the negative second power. I guess we've seen a few multiple choice questions at this point, and I just want to point out that all of these actually are the answer. Any one of them on a free response question would be accepted for full credit, but on a multiple choice situation, you might need to go a couple more algebra steps because there's a good chance that they would present this as one of the options and expect you to understand the connection. As far as question C, this is another product rule. Tangent times cotangent. Whoa, man. I was getting too zoom happy, I guess. Oh, I got to keep going. Although with this problem, you can do it much, much easier if you're paying attention. What you got inside of here is tangent times cosine. And the tangent is the sine over the cosine. This problem is really simple if you know your trig. And this is not even a difficult trig to know. Tangent is the sine of t over the cosine of t times the cosine of t. So what you need to recognize here is that the cosines actually cancel out, and you end up with the derivative of sine, which is just cosine. Like that. I'm willing to bet that if you went through the product rule and actually multiplied all that out and did all of the derivatives, you could do a bunch of trig identity work, get a bunch of stuff to cancel out, and it would be equal to just the cosine. But when in doubt, if you see something like that, that's got to set your alarm off that you can make it a lot easier for yourself. 627. We're going to use the calculator for this problem before you panic on this. Earlier, Jamal wrote the Riemann sum, all of that stuff, from 0 to 9 of 1/2 times this function to estimate the area under the curve for the function 3x minus 3x squared minus 2 over the interval from negative 3 to 2 using 10 rectangles. Just a quick review of this stuff. We got 10 rectangles. That's where the 9 came from right there. Also, the interval is from 2 to negative 3, so 2 minus negative 3 over 10, that's the 5 over the 10. That's where the 1/2 comes from in this problem right there and right there. And then as far as the negative 3 is the left bound. So in what you're seeing inside of the parentheses here is you're seeing negative 3 plus 1/2 times, or I guess delta xi, like that. So you're evaluating this area for that thing there. In order to make this happen on the calculator, we're just going to review these steps really quick. To make this Riemann sum happen, we're going to have to do a little bit of prep work. It's not going to be terrible, but we haven't done it in a while, so I would understand if you maybe dropped off the sigma notation boat for a while. The first thing we need to do is program in 3x squared minus 2 into y1, because that's the original function that we're dealing with, and we're going to need that. Into that function, we are plugging negative 3 plus 1/2 x, or 1/2 I guess. That's what we're plugging into this function. So you can think about this like a composite. This is getting plugged into this function. In order to make it happen on the calculator, we're going to change that x. We're going to use alpha f4. We're going to change that into a y2. So what this will do is it will actually run the negative 3 plus 1/2 x in y2 and plug that in to y1. That'll cause the sigma notation to actually operate correctly. Back out here on the main screen, let's actually set up the sigma. We'll go the summation here. We'll go from x equals 0 to 9. And right here in this space, we're going to first open a fraction and type the 1/2 for the and the change in x, delta x. And we're just going to multiply that times y1. Because remember, the way we programmed it is that y1 contains that other subcalculation in y2. So this should do the trick. This should make it happen. It's going to be about 29.375 or something like that. Can I get an estimation for this, please? Oh my gosh. How can I force it to be a mode? How about classic? Does that work? Oh, shoot. Hang on. Ah, rats. I want it to be a decimal. 235 divided by 8. 20, there we go. 23.375. I kind of like that answer, too. So for part A, the estimation that we get on the calculator is 29.375. That's probably a lot more time than I wanted to spend reviewing this because, again, you do not need to worry about this for the actual AP test. However, what I do want you to be able to see is the structure, because the next thing we're going to do is use the integral, which is a much better tool. The integral from -3 to 2 of the function 3x squared minus 2 dx. That's it. This is a much better way to do this problem, and the calculator can do it for us automatically. We're going to use the fn int. Oops, whoops. Let's go back to math type. Math print, please. God, I don't want to use the classic version for that. Fn int. We'll go from -3 to 2. I plugged this into y1, or I programmed the function into y1, so I'm going to use that. But you could just type in the function again, 3x squared minus 2 dx. Whoops. dx. Oh, shoot. There's no undo on this, is there? Beans. -3 to 2 of y1 dx. Bam. It's going to be, whoa. What did I do along the way here? If you do y1 dx, 3x squared minus 2. Is that programmed in there? Oh, whoops. I guess I can't do that because y1 involves that other fraction there too. That's why I'm getting a conflated answer. So don't do that, I guess. 3x squared minus 2. There we go, 25, which is a lot more reasonable because it's really close to what our approximation was. Again, the real big idea here I want to explore with this problem is to remember that integrals actually came from adding up a lot of tiny rectangles. And a lot of times the tiny rectangles are an over or underestimation. So the integral is the exact answer. 628, let's talk about logarithms and e to the x. And inverse functions too. Since e to the x and natural log are inverse functions, we know that e to the natural log of x equals x, and the natural log of e to the x equals x also. These things undo each other. Use these facts along with the properties of exponents and logarithms to rewrite each expression. So the best way to handle these problems, let's see. The first thing I would do in question A, there is a rule about logarithms that says that if you have a constant number times a log base b of something, of y, you can take that and kick it up in the exponent. This is the log base b of y to the x power. I'm going to do that right now. I'm going to move this 2 up here and rewrite this as e to the natural log of x squared. The reason why I want to do that is because now the e to the natural log part cancels out and the answer is just x squared, like that. B is even easier because the e to the natural log part can cancel out right now, and the answer is just the square root of x, so there's really nothing to worry about in that problem. E to the natural log of something cancels out, just the something is left. With question 7, here we have another one of these kind of like, we need to think about how we're going to rewrite this as the natural log of e raised to 1 power. It might be helpful right away to recognize that this is natural log of e to the 5x all being raised to the 1/2 power. And the nice thing there is that you can actually just multiply those exponents together. 5x times 1/2, you'll have natural log of e to the 5x over 2 power. That's another way to write the exact same idea going on here. And now the natural log of e can cancel out, and you're left with 5x over 2. And that's the answer to this problem. And we'll do a similar trick with question D. Actually, no, for question D, we're going to use another property of logarithms where if you have the natural log of a times b, or any log, it doesn't have to be a natural log, but any logarithm a times b, you can rewrite this as the natural log of a plus the natural log of b. It's a property of logarithms. So we're going to separate this right away into natural log of 5 plus natural log e to the x. And the natural log of e cancels out, so we have natural log of 5 plus x, and that's the only way to write that answer. So just like before, I'm going to have to make sure I make a note in class that you must be looking at the homework problems, especially in these first couple sections, because we're going to be reviewing some natural logs, some logarithms and exponential rules that we are going to need those to understand a couple things coming up down the line. Not that there's any complicated stuff happening here, but some stuff that you should review. Just keep it fresh in your head. 629, I'm kind of putting an asterisk next to. I don't know if it's going to make it into the final cut, but I just thought it was the last question anyway. So we've been skipping a lot of these, and I feel like this is a pretty accessible one. So you do see these problems on every AP test that you'll take too. So Let's let f of x equal this piecewise function. It's got a break at x equals 1. It's going to separate into two separate ideas there. The first question is, for what values of x is the graph non-differentiable, regardless of the values of a and b? So to do that, we're going to take a look at our two original functions. We're going to look at 3x to the 2/3 power, and we're going to look at a plus b times x squared. And we're going to take the derivative with respect to x of both of these. And specifically, we're going to think about what's going on at the number 1 right there, too. We want to make sure that these derivatives have to be the same. In order for the graph to be differentiable, these two things have to be the same when x is 1. So we're going to take a look at the derivatives, and then we'll start thinking about what's going to happen if we were to plug in 1 for x. So for this first one, we would have 3 times 2/3 x to the negative 1/3 power if we're looking at the derivatives. And here, since it's the derivative with respect to x, a just goes away and becomes 0. And the derivative of b times x squared would be 2bx. That's it. So a doesn't actually matter here. So if we're thinking about this, what we're looking for is places that would cause this to not have an answer, cause these derivatives to not exist or to not be the same. So if we simplify the one on the left, first of all, 3's will cancel out. You'll have 2 over the cube root of x, and this is as 2bx. Keep in mind, these are the derivatives. In fact, if I wanted to write f prime, which I do, f prime of x would be these derivatives. It would be 2 over the cube root of x for values of x that are less than or equal to 1, and it would be 2 times bx for values of x that are greater than 1. That's the derivative version of the original function. So, as far as places where the derivative wouldn't exist, well, one dead giveaway is the 0 down below. X cannot be 0. Because if x is 0, then the bottom of the fraction becomes 0, and that's not defined. So that can't happen. But 2bx, that has no problems at all. So I think that's the only issue with question A. So at question A, my answer is x cannot be 0. And as far as what happens to the graph at those points, I mean, maybe it might be worth taking a look at. I don't actually know off the top of my head, although I suspect it's going to be a cusp. So I'm going to go back into y1 and clear out our work from this problem. I'm just really worried about 2 over the cube root of x. Right there. I have no way of graphing the second equation because I don't know what b is, but I'll take a look at this one at least on a nice standard graph. At x equals 0, I think there's going to be a cusp there. Yeah. Oh, there's actually a break. There's a discontinuity happening there. Okay. Cool. So there is a discontinuity. Oh, no, sorry, that's not the original function. That is the derivative. Well, the original function would be 3x to the 2/3 power. So the derivative has a break, but the original graph, there's the cusp. There we go. Yeah. Okay. That's exactly correct. So there's a cusp in the original graph. For question B, determine the values of a and b such that the graph is both continuous and differentiable. Okay, so when it comes to continuous, this is our work for problem B. Let's start there. In order to be continuous, what we need is these two things. We need this 3 times x to the 2/3 power to be equal to a plus bx squared when x is equal to 1. That's the first thing, because at x equals 1, there's a break in the graph. We need these things to be the same then, so that it's continuous, so we don't have to pick up our pencil. Let's start there. So we need, well, I'm going to write down here, we need 3x to the 2/3 power to equal a plus bx squared when x is equal to 1. So let's think about this like a simple algebra problem. We're just going to plug 1 in for x. It's actually going to make this problem very simple. That means that 3 must equal a plus b. That doesn't help us too much, but it does give us one equation. And what's going to happen here is we're going to look at differentiability using our derivatives from the previous problem, or from part A, and we're going to get probably another equation that's either going to tell us what A is or tell us what B is, and that'll help us solve the other question. So let's talk about differentiable. Differentiable, it's the same game, except for this time we're looking at the derivatives. So we got our derivatives back in the first part right here. Oops, I wanted a highlighter, please. right here, and right here. Those are our two derivatives. And again, we need those to be the same when x is 1. So we need 2 over the cube root of x to equal 2 times bx, again, when x is equal to 1. So this looks complicated, but you're going to plug in 1 for x. It makes the problem much easier. This means that 2 equals 2b, which is another way of saying that b equals 1. And of course, if b equals 1 over here, that means that 3 is a plus 1, and that means that a has got to be 2. So the correct answer here is that a has got to be 2 and b has got to be 1. So you actually kind of boil this down into a little system of equations problem. The differentiability part is not so common on the AP test, but the continuity part is absolutely guaranteed. So think about those things. Hey, thanks for being in this video with me for you guys. Thanks for watching along with me. It's very important that we're looking at these problems, especially the ones dealing with logarithms and exponents. But you're going to do fantastic because you are smart and capable, and I'm just so proud of you for being here. So thank you very much, and I'll see you in the next video.